Hello and welcome. This is the Consulting Specifying Engineer webcast titled Design Considerations for Generator Distribution Switchboards, sponsored by Siemens. I'm your moderator, Amara Rozgis with Consulting Specifying Engineer and CFE Media and Technology. Here are some tips to get the most from today's webcast presentation. If you're experiencing problems with your slides or with the audio, please refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume of this webcast by controlling the volume on your own device or by adjusting the volume on the webcast platform. If you're having technical problems with the audio or with the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks. If you do need a technician, and if you have extra questions, you can type a message in the Ask a Question box and someone will get to you as quickly as possible. Technical questions will be answered in the Answered Questions box. Please type your questions for our speakers in the Ask a Question box on the left side of your screen. The Q&A session will begin in about 45 minutes. Today's webcast is being recorded and you'll receive an email with a link to the on-demand event. To download a certificate of completion, a PDF copy of this presentation, and a white paper on design considerations for generator distribution switchboards, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of the webcast. All right, now we'll hear a word from our sponsor, Siemens. Please take a moment after the video ends to allow for varied internet speeds. Thank you.
You don't see us. As factories keep rolling, power keeps running, transport keeps moving, water keeps flowing, data keeps streaming. But we're here, behind the scenes, keeping the backbone of the economy strong. Because American industry and infrastructure will never run on technology alone. It will always require a human touch.
All right, thank you to Siemens for sponsoring this event. Now we'll learn a little bit about our presenters, Gary Gluck and James Alvers. James has been a business development manager for Siemens low voltage distribution products since June 2018. He assists the electrical consultants in North Carolina to apply and configure cost-effective, efficient, and compliant electrical distribution solutions for major infrastructure projects. James previously worked as a data center electrical engineer at Hewlett-Packard EYP Mission Critical Facilities. He's worked in electrical infrastructure designs, specifications, and proposals, as well as the startup of HP's micro data center. He's also worked for Schneider Electric as a global account manager. James received his electrical engineering and computer science degree from the University of California at Berkeley. As an active member of the Santa Clara Valley IEEE, James has held the position of Vice Chairman for IASPES. Gary is the Western Region Business Development Manager for Siemens Low Voltage Distribution Products. In this role, Gary takes his experience in education over the past 42 years to assist engineers and contractors to optimize their designs in the areas of code compliance, equipment size, product performance, and cost. Gary has been with Siemens for 27 years and is a proud graduate of the University of Illinois. All right, Gary, let's get started.
Thank you, Amara. Okay, so today's presentation, we're going to talk about some of the challenges that we face with designing generator distribution switchboards. These challenges come in a variety of different shapes and sizes, and the first area that we're going to talk about will be, or among the topics we're going to talk about, will be equipment size. And if you've had any involvement with the design of these boards, you know that it is not unusual that they could be 10, 15, 20 feet in width, which creates problems of its own. Another issue that we run into is code assignment. Is the load 700 for emergency? Is it 701 for legally required? 702 optional standby? For those of you who are designing, we can kiss you when you put that information on the drawing associated with the breakers that it goes with. If not, put it with the transfer switch. We can figure it out. Next area, ground fault protection versus ground fault alarm. This is an area of confusion. Which do you use, even if you use them at all? So we're going to get into that. Coordination. When we talk about coordination, it's typically in the context of selective coordination. And the two areas where we're going to be running into this will be with emergency and legally required. And we need to appropriately pick the correct overcurrent device so that it coordinates with the downstream loads from the generator distribution switchboard. Then we come up with main overcurrent device. If you have one, where does it go? The code is a little bit vague as far as that goes, and we will cover that. Compliance with arc flash mitigation requirements in the NEC, which is 240.87 and 240.67 in the code. It's a little bit counterintuitive because there are some methods of achieving the selective coordination which would, in fact, maybe cause the system to shut down during a fault condition or an arc flash condition. And it's a little bit counterintuitive that, do we really want to have compliance with that? But those code sections really don't allow for any exceptions to that. So we'll get into that. When it comes to fire pump, then, how do we do that? The fire pump seems there's confusion between what's required in the normal part of the system versus the emergency part of the system. And so we'll talk about how that works with generator distribution switchboards. And then the final consideration will be that this presentation is going to be based on NEC 2020. Before you get excited that your state's not on 2020, don't worry. While there's been a lot of changes in 2020, the changes that would be applicable for what we're going to talk about aren't really affected by the content. So with that, I'm going to turn this over to James.
Okay. I'd like to begin with some basic reminders regarding electrical room design, since space is one of the biggest issues, obviously, for for generator switchboards. Keep in mind, it's a team effort. Therefore, it's crucial to involve all the members of the project construction team to ensure the equipment as configured has the proper working clearances, access for conduit and busway, and so forth, required overhead clearances. You need weight and mechanical support, obviously proper access and egress. And an important thing that sometimes gets missed is space for anticipated expansion. If you have future breakers, it means you may need a future ATS, and you need to consider the pathway for some of the wiring. Obviously, proper illumination and ventilation. So you have to get the whole team together And most importantly, as a vendor, we see quite a few different designs, and the AHJ is the ultimate interpreter of the code. So you need to make sure they're involved, and so that, something maybe we see in California here, may not be acceptable in, Florida or somewhere else. The picture you see in the slide shows a switchboard, and we're going to be talking about switchboards, not switchgear. So typically you can place them against the wall. There are exceptions on occasion. You see in this case some individually mounted insulated case breakers, and another section with some molded case. Group mounted breakers, both are okay for generator switchboards. Obviously, going to save space if you can use group mounted breakers in your design. This slide here is just some very basic information on electrical room workspace issues. So the part of the code that deals with this is 110, Requirements for Electrical Installations, Part 2. It's worth reading the whole code. That whole section, obviously. I'm going to highlight just a few things. Basically, the working space requirement, and there's also a dedicated space requirement. So the code has a table, 110.26, which allows you to, defines the working space requirement for both, the standard 122.08 or 280.47 boards. So for instance, if you look at the table, you can see that for a 122.08 board with the picture above, you need 3 feet in front of, let's say, a standard wall, a standard drywall. 3 feet in front of a concrete wall, even though it's grounded, typically. 3 feet in front of another 122.08 board. However, if you go to 480 and you go across look at the table and go read across, it becomes 3 feet, 3.5 feet, and 4 feet. And then it gets a little bigger if you're at 601 and above. So those working spaces are important. There's a dedicated space above the board that is 6 feet, that you're not allowed to have any kind of piping or duct work and so forth. That space is equal to the width and depth of the board. So there's no piping, ducts, leak protection apparatus, etc. above the board, 6 feet, or if there is a architectural ceiling before the structural ceiling, that's okay. Okay, but it's got to be 6 feet to the structural ceiling. Some quick basics on access. Of course, access is needed for maintenance, and et cetera. But one of the code's primary concern is access to provide egress in the area in the event of an arc flash incident. Minimum doorways are typically 24 inches wide by 6.5 feet high. But, bigger doors are always better. Remember, you got to maintain the equipment. You may need to add equipment or remove equipment. So you want to think about those things. Doorways that are, for switchboards over 800 amps, you will need personnel doors. Will need, listed panic hardware and open, outward to facilitate egress. One door is required for anything under 1200 amps. If you go over 1200 amps, or the switchboard is 6 feet wide, you need 2 doors unless you have double the working space in front and a clear path out. I don't show that drawing on this particular slide, but once again, it's all in section 110. So, basically you can see that proper sizing of the emergency switchboard is critical for the room. You don't want to oversize the board. Obviously you don't want to undersize it either. But. I apologize. I did not move the slide. So I apologize. That slide should have been up.
Okay.
Okay,
all right.
Go ahead.
Okay, so let's just do a quick refresher before we get to the an example that's going to highlight the concepts that I mentioned with the first slide. Let's just do a quick refresher on the differences between 700, 701, and 702. And to this, I owe a debt of gratitude to Pete Jackson, who's the AHJ in the city of Bakersfield, who explained to me something that should have been obvious to me all these years. And that is that 700, the emergency, are those systems that are designed to facilitate the exit from a building during an emergency situation. So included in that would be emergency lighting, ventilation, public safety communications, fire pumps. And then we're also going to throw in a non-commercial sense, certain industrial processes where there would be, where current interruption would be pretty disastrous. So that's 700. 701, legally required, those are going to be the systems that need to be functioning for people that need to be in the building. So whatever personnel might include first responders, other firefighters, other emergency personnel. So here's where we're going to find smoke evacuation systems. I'm also putting elevators in this section. Some of you might say, wait a second, elevators are part of the emergency system. There's a certain debate and it's really not a debate, it's really what is applicable or appropriate for a specific building. When you have elevators that are going to be needed for assisting the first responders, that's going to have the tendency to move those systems into 701. Then we have 702, and I realize when I'm looking at the slide that I committed the cardinal mistake of putting the word that I'm defining in the definition. So optional standby are going to be those systems that have been identified by the end user or the owner of the facility as being necessary to have emergency backup. So, and it's going to vary from business to business. It could be maybe refrigeration in one kind of business, could be data, could be security. So, but there's the common thread between those systems are going to be is that there's no code or government mandate to have these. It's just going to be purely something that's going to be appropriate for that business. So let's look at a single line diagram that illustrates a typical generator distribution switchboard. Now, this particular single line came across my desk with the question that typically accompanies just about everything that comes across my desk, which is how do we optimize this board? Because if we go by what's been drawn, this board, it's 6 sections, and if we figure that on average, it varies among manufacturers between, let's say somewhere in the vicinity of 3 feet. I mean, the switchboard could be 18 feet wide. So, the question comes to me, what can we do with it? So let's just look at what's on this single line diagram. In the upper right-hand corner, we have the generator, and there's also a separate feed to the load bank. And that part we're happy with. We would appreciate it when the load bank is handled upstream from the generator switchboard. Just one less section that we have to deal with. And things just work out better that way. Okay, so then you come in, on the far right is the fire pump, okay? Then we have the incoming feed main breaker from the generator. Then we have the legally required, so I'm going right to left over here. Then we have a feed for life safety, followed by a feed for the elevator, and then the surge protective device. Okay, so that we have all of these loads. There's no optional standby in this particular example. Okay, so we're going to look at this section by section. So on the far right, I have that fire pump and I've got the incoming section. But before we get to those, I want to look at what the actual information that's specific to that switchboard shows. And the first thing that we see is that the engineer has called out 100,000 AIC. I was at a seminar several years ago, and Paul O'Hara, who is from Cummins out in California, mentioned to me that the maximum fault current that a generator is going to put out is going to be 10 times what the current rating of that generator is. That's going to be the maximum. So if we look at an 800 amp output from the generator, the maximum fault current for that switchboard is ever going to see is 8,000 amps. So going with 100,000 is a bit overkill. There is a substantial cost savings tailoring the distribution closer to 8,000. The engineer also shows 3,000 amp cross bus. There's really no reason. We have one source coming into this switchboard. There's no reason that we need to oversize the bus. Let's just stick with 8,000 amps for that purpose. Excuse me. All right. The incoming section shows a 700 amp trip with an 800 amp frame with ground fault protection. Excuse me. Okay, ground fault protection in this application is undesirable. NEC 700.6, and wait, let me just backtrack for a second. When I see ground fault protection, my assumption is going to be that we're talking about ground fault alarm and trip. Okay, so going back to my bullet points, 700.6 discusses the use of ground fault alarm. That is something that is desirable in an emergency generator distribution switchboard. The criteria that we see typically that people use is similar to the criteria that we see in 230.95, which obviously it applies to service entrance board, and this isn't a service entrance board, but if we typically will see ground fault protection, 1,000 amps and above, and at 480Y. So, in this particular case, ground fault protection could be eliminated from an NEC perspective. And as I said, ground fault alarm may be desirable, and we see it shown on drawings in a variety of different forms. GFA for ground fault alarm, GFM ground fault monitoring, LSIA, long time, short time, instantaneous alarm. So, and then one other point, I noticed that somebody had asked the question asking for clarification between group mounting and unit mounting. What we're seeing on the single line are unit mounting. These are sections where the only breaker is the only item in that section will be just a single breaker, as opposed to sections where we're able to panel mount and have multiple breakers in a single section. So hopefully that answers that question. And, okay, this is my question as well. So does the main breaker require a separate section? Now, this is an area where the code is not specific. It really does not address the question of where do those incoming feeders, where should they go? The NEC, as I said, skirts the issue. And if you ever see any of my presentations where I say standard industry practice suggests, that means I've called my counterparts with Schneider and Eaton and asked them what their thoughts are. So in this particular case, we've actually all come to the conclusion that if you've got main lugs, those incoming cables can go pretty much anywhere in the generator distribution board. If you have a main breaker, we say, you know what, put that in a separate section. So I'm not saying there's any specific rhyme or reason, but that's what we've arrived at. And that does seem to meet the requirements of the engineer of record, and AHJs that we've run into have not objected to that process. Okay, is this Mike? I think this is, no, this is James. James, it's back to you.
So does the fire pump need its own section? And it doesn't. The fire pump is kind of lucky. It can reside in two different sections. It can reside in the, excuse me, I'm thinking of elevators, I apologize. The fire pump is explicitly stated in NEC 700 in the, right in the code as an emergency load. So it does not need its own section. It can be there in the same section as the emergency loads. In this case, the breaker has been sized in accordance with NEC 695.4B 2B. So one thing to note on this particular one line is the ATS being fed by the fire pump has been oversized to 1,000 amps. And you'll see it here. And the reason for that is that the fire pump is tapped from the normal side. And, you have a fault current there at 69,000. So this switch may be overrated just to accommodate the normal side. 700 emergency loads. Engineers sometimes refer to these loads as life safety. And that's kind of understandable since the article explicitly states it's essential for safety to human life. However, this label is really reserved for healthcare generator boards, and that's defined in Article 517. So in this particular case, the one line should be revised to say emergency systems. Assuming these are emergency loads, this breaker would be grouped in a section which would also include the fire pump, as I described earlier. And that's listed in 700.2. So elevators are actually specifically mentioned in Article 700, but as Gary mentioned, they often fall into Article 701 because they are used for first responders. So that is something that comes out of the informational note in Article 620.91. So this is very common, and in this particular example, we're going to classify the elevator breaker into a 701 load. Once again, let's look at fault current. You'll notice here at this ATS, the engineer has said there's a fault current of 44,442 amps. So this ATS is probably not going to be able to meet that requirement. It's 150 amp 4-pole ATS. Most likely a fuse would be needed somewhere ahead of that ATS to meet that requirement. I'm going to talk more specifically about ATSs in a little bit here. So NEC 700.8 requires that emergency loads be equipped with surge protection. The engineer has included this in the leftmost section, and it's a separate section. This dedicated section can probably be deleted. Most manufacturers don't require a separate over-circuit protection device. It's included in the SPD. And for instance, here's an example of a section with a main breaker with the SPD mounted above the main breaker in a compartment. And it would serve the whole board. And that's fairly typical for all switchboard providers. The code doesn't describe the surge protection device. It basically just says that it should be UL listed. And what you want there is, at the minimum is a UL 1449 4th edition SPD. And then as an engineer, it's good to specify ratings and features, based on the particular location and application you're in. So, probably something more stringent in Florida than in California. NEC 701 legally required loads. This one line shows one breaker for legally required loads. It doesn't show anything for 702 loads, which are the optional standby. But if if there were breakers and he had showed them in separate compartments for those loads, those breakers could be combined with the legally required loads. The particular code reference for that would be 701.10 and 702.10, which basically state that wiring shall be permitted to occupy the same raceways, cable boxes, cabinets, and other general wiring for both, and that's true for both the legally required loads and the optional standby loads. So I know we're primarily talking about switchboards, but ATSs are a huge consideration for these switchboards. The code requires that they be electrically operated and mechanically held for emergency applications. And they're listed for system use. What that usually means is you need a UL 1008 ATS. It's very important to consider grounding and your neutrals for generator switchboards. Usually this is solved if you use 4-pole ATSs. So if you specify 4-pole ATSs and you want to make sure the fourth pole is not just a solid neutral, but an actual switching pole, you can avoid a lot of the issues with grounding and neutrals. If you need 3-pole ATSs or you need closed transition, you really need to consider, all your grounding and neutral and bonding issues. You perhaps will need modified differential ground fault or 4-pole breakers. With modified differential ground fault, you'll need to, obviously wire to the normal system to look at grounds on that side. So, that may affect placement of the board and things like that. The other thing to consider with ATSs is withstand ratings. Some vendors require specific breaker pairings to achieve the withstand ratings. So for instance, there's an example here of a withstand rating chart with the paired breaker associated for that particular ATS. Other vendors use what's called a 3-cycle rating, where they have a specific rating that is not tied to a specific breaker, and you can use any breaker that has the right AIC and amperage. Sometimes that's better. Sometimes sometimes using the chart is better. It really just depends on the application and selectivity, selective coordination. You need to also consider bypass isolation for maintenance. So there's a picture of a ATS there. Under that ATS, if you had bypass isolation, you'd have more hardware so that you can bypass that ATS and actually service it, while still keeping your system running. So now I'm going to show some possible switchboard constructions. The first example is the optimized switchboard based on the one line. The second drawing shows what happens when section 700.3F is taken into consideration. Given that this switchboard has a single generator feed, there needs to be a provision for backup generation, for a backup generator when the main generator is taken offline for maintenance. So adding an extra breaker interlocked with the main generator breaker would be code compliant. So here is the optimized switchboard, EMDB. So what was shown is 6 sections can be configured into 3. The board is now rated 800 amps. The interrupting rating has been changed to 22,000 amps. This is going to save, obviously, money, but may save a bit of space as well, depending upon the configuration. Ground fault protection, as we mentioned, is not required for this board. Arc flash mitigation is not required because everything's under 1200 amps. Section barriers are required, and that's a good thing to put in your specification to make sure you get those section barriers. Ground fault protection. Okay, here's a caveat on ground fault protection. In the code, it's very specific that it's not required for 700 and 701 loads. However, as an equipment vendor, we defer to the engineer of record in the AHJ for the 702 loads because that wording is not specifically in the 702 section. So we've seen it go both ways. Selective coordination is required for the 700 and the 701 loads. It is not required for the 702 loads. Here's a second configuration to help meet Article 700.3F. So here I allow connection to a temporary source power for maintenance and repair. The section on the right has another, main generator breaker. It could be a temp generator. It could be a second generator. They are Kirk-key interlocked. Once again, you have to consider grounding. Modified differential ground fault or 4-pole breakers may be needed. Another option for that last section is to have cam lock connections. So this particular section can be, just part of the overall switchboard, or it can be mounted remote, in which case you'd need some lugs on the main switchboard. Often it's outside, so it's NEMA 3R. Somebody's moving my slides here. Often it's outside, so it's NEMA 3R. There's covers over the cam locks so that when the temp generator is connected, it remains NEMA 3R rating. There's also options you can get so that you can get lugs for type W welding cable as a secondary connection to a temp generator. Once again, main breakers are Kirk keyed. Once again, consider grounding. Gary?
Thanks, James. I'm going to talk just for a little bit about distribution switchboards for healthcare. And for that, we're going to consider this switchboard that came from a project. This is a hospital in California. It's got the OSHPOD number at the very bottom, which it's usually a giveaway over here. We look at the board differently for healthcare than we do in the commercial world, because from a hospital perspective, everything is emergency. And we actually use the term essential electrical system for these generator distribution switchboards. And the categories are going to be different. I'll quickly do a refresher in a second, but just taking a quick look at the switchboard, we got the incoming feed from the generator. We've got feeds going to what's termed life safety. We got a feed going to critical and a feed going to equipment. There's also some spares and spaces that have also been identified by the engineer. Okay, so just a quick refresher on the categories. 517.33 is life safety. This is pretty analogous to what is to 700, because it's going to facilitate all the loads that are necessary to exit the building during an emergency. And that's that'll consist of emergency lighting, exit lights, etc. 517.34 is critical, and those are those loads that have an immediate impact on the well-being of patients or are essential to the clinical functionality of the healthcare facility itself. So we have a lot of equipment here. We have nurses, call stations, operating room equipment, etc. The final category is going to be equipment branch. Essentially serves the mechanical loads that are required for the support of clinical activities. A lot of HVAC and other mechanical loads would be found in this section. All right, just a quick observation about this design. The three categories shown, life safety, critical, and equipment, constitute, like I said, the essential electrical system defined in 517.26. Ground fault monitoring may be desirable, but it is not required by the NEC per reference to Article 700. And generator distribution boards are not exempt from compliance with arc flash mitigation. Any breaker that's 1200 amps or larger may need to comply. And it's best to choose a method that does not interfere with the system coordination. So zone selective interlocking is actually a really good choice. It just, for compliance, as it does not interfere with the normal coordination in the system. James, I think I had you, but I'll continue with this, okay? All right, so here's,
Okay.
All right, so switchboard configuration 1, just a couple of notes. Default current rating seems excessive at 30,000 for the same reason that it was excessive in the earlier example, just due to the capacity of the generator. The main breaker and the equipment branch include arc flash mitigation, and we're using an energy reducing maintenance switch. The SPD not required in a separate section. The breakers are coordinated, and individual metering is shown. However, group metering is possible with many vendors. And then this is a California thing. Due to OSHPD, each one of those categories, life safety, critical, and equipment, each need to be in its own section. That may not be the case in other jurisdictions, but it is a situation in California.
So I want to add one thing to that slide here.
Oh, go ahead, James. Go ahead.
So the 1200 amp distribution breaker in the equipment branch is actually a 1200 amp frame with an 1000 amp trip on the one line. So if that breaker were a standard thermal mag with a non-interchangeable trip, you would not need arc flash protection there. Often these breakers are selectively coordinated, so you may have a stall estate breaker there, in which case, even at 1000 amp trip, you would need the arc mitigation.
Okay. All right. Just a couple of final words about this configuration, and then we'll just move on to the final topic of switchboard size. Sections 3 and 4 can be combined outside of California. Those are going to be your critical and your equipment. And then when you're dealing with spares, please let us know what category they're going to be applicable to. It absolutely makes our life so much easier than trying to guess, because inevitably we're going to guess wrong. And then, as we mentioned before, consider grounding. Spares and new breakers should feed 4-pole transfer switches, and consider room for future ATSs and downstream connections. Okay, so then the final topic is going to be when space becomes an issue, and frankly, when is it? On average, as I mentioned at the beginning of the presentation, switchboards can be anywhere from 10 to 20 feet. If space is truly at a premium and the system is not that large, you can use wireway and enclosed breakers, in order to achieve specific size. And that's going to be a fairly narrow solution. But in most cases, with most of the projects that we see, we're going to exceed that, and we're going to need to use switchboard construction. And and this picture illustrates, what we could typically see. Here's a switchboard that it's not tied to any specific example we gave, but it's excuse me. Here's a board that's going to be 369. It's going to be 11 feet wide, and manufacturers have come out with new narrow width sections, Siemens included, and the illustration on the right shows such a board where we're able to shrink 32-inch wide sections down to 25-inch sections. So that's one strategy that we can employ for reducing the overall width. And with that, Amara, I think we're going to turn this back to you if anybody has questions or comments.
Yeah, exactly. Thank you so very much. And now Gary and James will answer questions from the audience. Please type your questions for the presenters in the Ask a Question box on your screen, and we will get to as many as time allows. Questions that we don't get to today will be posted online at the Consulting Specifying Engineer website at www.csemag.com with the archived version of this webcast. And please remember to download a certificate of completion or a copy of the presentation or the white paper use the Event Resources tab on the left side of your screen. And for that additional information, the white paper covers design considerations for generator distribution switchboards that is available as part of the resources to download. Gary, this first question is for you. Where is the ideal location for a switchboard?
Okay, thanks, Amara. The ideal location, I mean, there's some basic considerations that we can take. For us, indoor is better than outdoor, and a lot of times we have to take our cues from the architect, because sometimes we're just given some basic information and we'll size it accordingly, and then the architect will chime in. And so a lot of times we're going to be at the architect's mercy as far as where that ideal location is. But there is one other consideration that is something that, something we don't always think about, and that is that if we have to have the main breakers between the emergency and the normal communicating with each other, like we would under a condition of modified differential ground fault protection, then you may want to consider having the two boards fairly close to each other, so as opposed to on opposite sides of the building. Okay?
Got it. Good to know. Thank you. James, this next question is for you. When do you specify a manual transfer switch?
So you must specify automatic transfer switches for the 700 loads and the 701 loads. However, you can, if desirable, use a manual transfer switch for the 702 loads. And then on healthcare, I have always only seen automatic transfer switches there. I know that in NFPA 99, they go through the requirements for transfer switches, and they include both automatic and non-automatic. But typically in healthcare, I can't recall ever seeing manual transfer switches for the loads. But obviously in 702, those are optional loads. So, there are loads that you as a engineer or user have decided they need to be standby. So you have a choice of making them automatic, using automatic or manual transfer switches.
All right, thank you. Let's see here, Gary. A lot of good questions coming in. If you do have a question for one of the presenters, please type your question in the Ask a Question box, and we'll get to as many as we can today. So Gary, next one is yours.
Okay.
What are some nice bells and whistles that you would include in a specification for switchboards?
Other than Shelby Siemens no equal, no. I think that one that James and I were talking about that I think would be really appropriate and provide value to the end user would be having a thermal monitoring system built into the generator distribution switchboard. Most manufacturers offer these, and so what it's going to allow for this critical switchboard, it's going to allow 24/7 monitoring of the internal temperature of the switchboard at all of the key points within the switchboard. So it becomes an early warning system against possible problem down the road. So from our perspective, that's a really great, useful, cost-effective bell and whistle to add to a system.
All right, very good, thank you. James, I'm gonna send another question your way. Can the permanent connection to a temporary load bank requirement be incorporated into a switchboard?
Usually that's a separate board. So on the one line that was shown early in the presentation, there was a breaker there coming out of the generator for connection to a load bank. And that's typically the best way to do it. Somewhere you got to tap so that you need to go to the load bank. The generator board itself, feeds the actual loads, so you have to tap in front of it. So typically that might be a single section, very similar to the section that I showed for a temporary generator, except this time you're going to be, it's going to be an output to a load bank. This board can be just lugs with a breaker, or it can also have the cam locks as we showed for the generator board. So you can do it either way. But it's typically a separate board. It can be in the same room, or it can be somewhere else. That's really up to the physical criteria of the application.
Right. Okay. Thank you. Let's see here. Gary, another question for you. This is a clarification. Do you mean 8,000 amps or 800 amps for a bus rating?
Okay, so in this particular application, 800 would be the bus rating and 8,000 would be the minimum fault current rating. So I'm sorry if I wasn't clear on that point.
All right, thank you for that clarification. Let's see here. I think, James, this might be a good one for you. Where do fire alarm systems go? Can you tackle that one?
The fire alarm systems are part of the fire pump, and they go into the NEC 700 section. You can have them there. They don't need their own section. You have them there with the other emergency loads as well. Great,
thank you. All right, and it looks like we have time for just one last question. Gary, this is kind of a clarification again. LSIGA, can you define that? Arc Reduction Maintenance System, or can you go through that?
Sure, Amara. I saw that question, and I was hoping that I'd have the opportunity to answer that. I'm not sure that there's been like a steady state that has developed as far as the labeling of these electronic trip units. So what I've seen is LSI, we all know, long time, short time, instantaneous. We'll put a G at the end if it's ground fault, protection, and trip. We'll put an A at the end if it's alarm. And I think what the author of the question was concerned about is, well, where do you put the arc flash? I've seen it put ahead of the L. So if you're looking for arc flash mitigation and you want the ground fault alarm, okay, that would be ALSIA. So that would be, when I see that, then I understand that. So there's a little bit of confusion with the two A's and what they mean.
Thank you for clarifying that alphabet soup.
Okay.
All right. Well, thank you for those great questions, too, to our audience. And thank you to our fantastic speakers, Gary Gluck and James Alvers, for their time and expertise today. And I'd also like to extend a special thank you to our sponsor, Siemens, for sponsoring today's event. Now that we're just about done, we want to hear how we did. An exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it. We use this information to improve future webcasts. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, I'd like to thank you for attending. This now concludes our webcast. Thank you and goodbye.